Hey everyone, welcome to this new story. Today, we look up at the night sky and imagine a world with not one, but two moons. Right now, our single moon guides the tides, lights the night, and marks the passing of time. But what if another moon appeared out of nowhere? How would the oceans react? How would the sky change? Already, the moon's pull shapes life on Earth in ways we barely notice. With two moons, forces would clash, tides could rise higher, and shadows might move strangely across the land. Night after night, the two moons could dance across the sky, their phases overlapping, their light combining, or even fighting for dominance. In this video, we explore what happens when Earth suddenly gains a second moon and what such a change could mean for life, weather, and the rhythms of our world. The moon is the only natural satellite of Earth. Its diameter measures roughly 3,474 kilometers, about one-fourth the size of Earth. The moon's mass is approximately 7.35 times 10 to the 22nd kilograms, which is only 1/80th that of Earth. It orbits at an average distance of 384,400 kilometers from the planet. This distance is not constant. The moon follows an elliptical path, so at perigee it comes closer to 363,300 kilometers, and at apogee it moves farther, around 405,500 kilometers. Its orbital period is about 27.3 days relative to the stars. This means the moon completes one full circuit around Earth in just under a month. The moon has a gravitational pull that directly affects the Earth. The most visible effect is the movement of oceans. Tides rise and fall due to the pull of the moon. High tides occur where the ocean bulges toward the moon. On the opposite side, inertia and the pull of the moon create a second bulge. Low tides appear in between these areas. Tidal differences are strongest during full and new moons, when the sun and moon align. These are known as spring tides. When the sun and moon are at right angles, the tides are weaker. These are called nap tides. The moon also stabilizes Earth's rotation. Its gravity prevents large swings in the tilt of Earth's axis. Without the moon, the tilt could vary by tens of degrees over millions of years. This would change the strength of seasons dramatically. Currently, the tilt stays close to 23.5 degrees, keeping seasonal patterns consistent. The moon's presence slows down Earth's rotation gradually. The length of a day increases by roughly 1.7 milliseconds every century. Over billions of years, this has extended the length of a day from about 6 hours in the early Earth to 24 hours today. The moon itself is composed mainly of silicate rock. Its surface consists of highlands and darker plains called maria. The highlands are older, heavily cratered regions formed over 4 billion years ago. The zone maria are basaltic plains created by ancient volcanic activity. The craters are a record of billions of years of impacts from asteroids and comets. Unlike Earth, the moon has no atmosphere to erode or weather these features. The lack of air and water preserves the surface in almost the same state for long periods. Temperature on the moon varies widely. On the lunar day side, it can reach about 127 degrees Celsius. During the long lunar night, temperatures drop near minus 173 degrees Celsius. The absence of an atmosphere causes extreme swings. This also affects the surface materials, gradually breaking rocks into finer soil called regolith. The regolith covers most of the moon and can be several meters thick in older regions. This layer contains tiny fragments of rock, dust, and particles formed by past impacts. The moon rotates on its axis at the same rate that it orbits Earth. This synchronous rotation keeps the same side facing Earth. This near side shows large maria and prominent craters, while the far side has far fewer dark plains. Scientists only observed the far side fully after spacecraft flew beyond the moon's orbit. The difference in terrain between near and far sides is linked to variations in crust thickness and impact history. Lunar gravity measurements indicate uneven mass distribution beneath the surface. These anomalies, called mascons, are concentrated beneath Maria. Mascons affect satellite orbits and reveal the moon's internal structure. The moon has very weak gravity, about one-sixth of Earth's. Objects weigh much less on its surface. Astronauts can jump higher and carry heavier loads relative to Earth. The lower gravity also influences how dust and small rocks move after impacts. Small particles can remain suspended longer and travel farther before settling. This affects landings, surface operations, and the evolution of lunar craters. The moon's orbit is slowly expanding. Tidal interactions transfer energy from Earth's rotation to the moon's orbit. The distance increases by approximately 3.8 centimeters per year. Over millions of years, this alters Earth moon dynamics, slightly weakening tides and slowing the rotation of Earth further. The gradual separation also changes the timing of eclipses and the apparent size of the moon in the sky. Observations of the moon have been conducted for thousands of years. Early astronomers recorded its phases and motions, connecting them to calendars and seasons. Lunar eclipses occur when Earth casts its shadow on the moon. This demonstrates the alignment of Sun, Earth, and Moon. Solar eclipses happen when the moon blocks the sun's light, a result of the moon's size and distance appearing almost equal to the sun from Earth. Both types of eclipses provide measurable insight into orbital mechanics and Earth-Moon relationships. The moon also contributes to the stability of Earth's climate. By regulating axial tilt and tides, it indirectly influences ocean circulation and weather patterns. Ocean currents redistribute heat, and tidal mixing affects nutrient cycling. The moon's gravitational pull even causes minor bulging in Earth's crust. These bulges move slightly as Earth rotates, producing additional tidal effects on both oceans and the solid Earth. The moon's role in these processes has been continuous for billions of years, shaping the environment in ways subtle but significant. The moon's presence defines much of the natural rhythm on Earth. Daily and monthly cycles correspond with its motion. Its phases have guided biological behaviors in various species. Reproduction, migration, and feeding patterns of some animals correlate with moonlight and tidal cycles. The moon's gravitational pull subtly impacts even atmospheric tides, which in turn affect wind patterns. These interactions are measurable and persistent. Scientific study of the moon continues with orbiting satellites, landers, and rovers. Lunar missions map surface features, measure gravity, analyze soil composition, and detect water ice in permanently shadowed craters. Remote sensing instruments detect variations in surface minerals and monitor temperature changes. Future missions aim to investigate the moon's interior and the long-term evolution of its orbit and rotation. All observations contribute to a detailed understanding of the moon as an active part of the Earth system. The moon's orbital plane is tilted about 5 degrees relative to Earth's orbit around the sun. This slight tilt affects the occurrence of eclipses and the apparent path of the moon in the sky. Its orbit is not fixed. Gravitational interactions with Earth, the Sun, and other planets induce small variations called perturbations. These changes influence long-term stability and provide insight into celestial mechanics, which are applicable to other planetary systems. The moon's role extends beyond simple orbit. Its mass and position affect Earth's precession, the slow wobble of the rotational axis over roughly 26,000 years. Precession alters the orientation of the equinoxes and shifts the location of celestial poles. This movement interacts with seasonal and climate patterns. The moon's stabilizing effect minimizes extreme variations, contributing to the predictability of day length and seasonal cycles essential for ecosystems. Surface geology reveals a record of the early solar system. Crater counting allows scientists to estimate the age of different regions. The highlands are the oldest terrain, while Maria are younger by hundreds of millions of years. Impact basins provide information about asteroid populations and collision history. Samples returned by astronauts show isotopic compositions similar to Earth, supporting theories of formation through a giant impact early in the solar system. The moon is also a reference for time. Its phases provide a natural cycle of about 29.5 days from new moon to new moon, known as the synodic month. Ancient civilizations aligned calendars, agricultural cycles, and festivals with lunar cycles. Modern science uses precise measurements of lunar motion to calibrate timekeeping, satellite navigation, and spacecraft trajectories. These measurements rely on laser ranging experiments that bounce light off reflectors placed by Apollo missions, providing millimeter scale precision in distance measurements. Lunar exploration has confirmed the absence of a global magnetic field. Some rocks retain localized magnetization, suggesting ancient dynamo activity. The lack of a strong magnetic field contributes to surface exposure to solar wind and cosmic rays. This exposure gradually alters surface materials, sputtering atoms and forming thin layers of implanted gases. These processes occur over long timescales and inform understanding of space weathering on airless bodies. The moon's composition and orbit make it an essential partner to Earth. Its mass and gravitational influence affect tides, rotation, axial stability, and even climate over geological time. By observing the moon and its interactions, scientists understand the broader context of planetary systems, the dynamics of orbital mechanics, and the forces shaping terrestrial environments. Its presence is a defining factor in Earth's physical and environmental stability. If Earth were to have a second moon, the dynamics of its orbit would be governed by the same principles that control all objects in space. Gravity, mass, and momentum determine the motion of both moons and Earth. Each body exerts a pull on the others. The force of gravity depends on the mass of the bodies and the distance between them. A second moon would experience the pull of Earth, the original moon, and the Sun. Similarly, its presence would slightly alter the path of the first moon, causing subtle shifts over time. The balance of these forces determines whether the second moon can maintain a stable orbit or drift away. There are several possibilities for where a second moon could orbit. It could occupy a co-orbital path, sharing the same general orbit as the first moon, but positioned ahead or behind at a stable point. Another possibility is an orbit closer to Earth inside the current moon's orbit. A smaller inner moon would complete a revolution more quickly, and tidal forces would act differently. It could also orbit farther away, outside the current moon's path, taking longer to circle Earth. Each configuration has specific conditions that must be met for stability, including the right speed and distance to counter gravitational forces. Lagrange points offer another orbital option. These are positions in space where the combined gravitational forces of Earth and the Moon create regions of equilibrium. A small object placed at a Lagrange point can remain relatively stable with minimal propulsion. For a second moon, the L4 and L5 points in relation to Earth and the original moon could allow it to remain in a fixed relative position, forming a triangular arrangement. These points are not entirely free from influence. Perturbations from the Sun and other planets can slowly change the orbit, requiring careful calculation to maintain long-term stability. Mutual gravitational interactions between two moons create resonance effects. The timing of their orbits can become linked, forming a pattern where specific alignments repeat at regular intervals. These resonances can stabilize motion, or in some cases, amplify orbital shifts. If the moon's orbital periods are simple ratios of each other, resonances may lead to repeated gravitational nudges. Over thousands or millions of years, these interactions may alter the shape of the orbits, making them more elliptical or causing slight tilts relative to the equator. The second moon's mass plays a role in how strongly it influences the first moon. A small moon would exert minor changes, barely affecting the existing tides and orbital motion. A larger moon, closer in size to the current moon, could generate noticeable shifts. The original moon's orbit could elongate or tilt slightly, and tidal forces on Earth could increase. Calculations of such interactions require accounting for both the immediate gravitational pull and cumulative effects over time. Even small forces act continuously, producing measurable changes. Tidal locking is another factor to consider. The current moon is tidally locked, showing only one face to Earth. A second moon might eventually experience similar effects. Gravitational forces between Earth and the new moon would slow its rotation until one side always faces the planet. The time required for tidal locking depends on the moon's size, distance, and rigidity. Over millions of years, both moons could become tidally locked, maintaining predictable orientations that influence illumination patterns and gravitational interactions with Earth. Orbital stability is not guaranteed. Multiple moons create a more complex system with paths sensitive to initial conditions. Slight differences in velocity or position can lead to chaotic motion over long periods. Simulations of two moon systems show that some orbits are stable for millions of years, while others become unstable, leading to collisions, ejections, or shifts in orbital distance. The Sun's gravity adds another variable, pulling on both moons and slightly perturbing their paths. Planetary alignments can amplify these effects, producing irregularities in the orbit over centuries. A second moon would also affect the timing of eclipses. The alignment of three bodies, Earth, the original moon, and the new moon, creates more complex patterns of shadow and light. Solar and lunar eclipses could occur more frequently or in unusual sequences. The timing and location of these events would depend on the orbital planes of both moons, their relative distances, and the interaction of their gravitational pulls. Eclipses provide a natural measure of orbital mechanics, and a second moon would add new variables to the system. Inclination or tilt of the orbital plane is another factor in maintaining a stable path. The second moon could orbit in the same plane as the current moon, minimizing gravitational conflicts. A slightly inclined orbit could reduce resonance effects, but increase the chance of crossing paths during long-term precession. The relative inclination affects how often the moons come close to one another and the strength of their mutual perturbations. Careful positioning in three-dimensional space is necessary for long-term stability. Orbital eccentricity, the degree to which the orbit deviates from a circle, influences tidal forces and gravitational interaction. A circular orbit produces steady, predictable forces, while an elliptical orbit causes variations in distance and gravitational pull. The closer the second moon comes at perigee, the stronger its effect on tides, the original moon, and the Earth's rotation. Eccentricity also determines how quickly perturbations accumulate, with more elongated orbits often requiring longer-term adjustments to remain stable. The combination of these factors, mass, distance, orbital plane, eccentricity, resonance, and tidal locking, defines the overall dynamics of a two-moon system. Mathematical models simulate potential configurations, calculating gravitational forces at every point in the orbit. Even small differences in parameters can create significant long-term changes. Astronomers study similar systems around other planets, such as Jupiter and Saturn, where multiple moons interact in complex patterns. These observations help predict the likely behavior of a hypothetical second moon around Earth. A second moon could also interact with artificial satellites in near-Earth space. Its gravitational influence would slightly modify the orbits of spacecraft, requiring adjustments for long-term missions. Communication satellites, GPS systems, and space telescopes would experience minor but measurable changes in orbital parameters. Engineers would need to consider these effects when planning trajectories and maintaining stable satellite networks. Over extended periods, gravitational interactions could lead to migration of the second moon. Tidal forces could push it farther from Earth. similar to the current moon's slow outward movement. Resonances might cause gradual shifts in orbital distance or eccentricity. In some scenarios, close encounters with the original moon could slightly alter trajectories, producing new orbital patterns or requiring stabilization. These processes occur over millions of years, with measurable but gradual changes that maintain overall system coherence. In summary, the addition of a second moon introduces a web of gravitational interactions that affect Earth, the original moon, and the new satellite. Orbital mechanics dictate positions, speeds, and resonance patterns. Stability depends on mass, distance, and initial conditions. Lagrange points, co-orbital paths, and inner or outer orbits each present advantages and challenges. Tidal locking, perturbations, and eccentricity shape long-term evolution. Even small forces acting continuously produce significant outcomes over geological time. The resulting system would be more complex than Earth currently experiences, with implications for tides, rotation, and orbital dynamics that extend far into the future. The presence of a second moon would alter Earth's tides in ways that are predictable yet complex. The oceans respond to the gravitational pull of every body in space. Currently, the moon causes the primary tidal bulges. A second moon would add a second, independent bulge. When the two moons align on the same side of Earth, their gravitational forces combine, producing higher tides. These are stronger than normal spring tides. When the moons are on opposite sides, the forces partially counteract each other, producing lower tides than expected. The timing of high and low tides would shift accordingly, creating new cycles of ocean movement. The frequency of tides would also change. Instead of two high tides per day, variations could become irregular. Depending on the distance and orbital speed of the second moon, some regions might experience 3 or even 4 noticeable tides over a 24-hour period. In other areas, tidal ranges might become smaller or larger than usual. These changes would vary geographically. Coastal shelves, bays, and estuaries respond differently based on local depth and topography. The interaction of multiple tidal forces would produce complex patterns, with high and low points occurring at different times across the globe. The amplitude of tides would fluctuate more dramatically. Regions near the equator, where centrifugal effects combine with lunar pull, might experience extreme highs and lows under certain alignments. Tidal resonance, where the natural oscillation of a bay or sea matches the timing of the moons, could amplify the effect. Large bodies of water, like the North Sea or the Gulf of Mexico, could see stronger tidal peaks, while smaller inland seas might experience less noticeable changes. The movement of water across the continental shelves would increase, transporting sediment and altering coastal morphology over long periods. Ocean currents respond to tides, as well as wind and temperature gradients. A second moon would modify tidal energy distribution, subtly altering the flow of currents. The Gulf Stream, Kuroshio Current, and an Arctic Circumpolar Current could experience slight changes in speed or direction. Even small modifications in these major currents would influence the distribution of heat across the planet. Warm waters might reach higher latitudes, while cooler waters circulate differently, impacting regional climate patterns over time. Coastal erosion would also be affected. Stronger tidal forces increase the energy acting on shorelines. Over decades, cliffs and beaches would wear down more rapidly in regions experiencing higher combined tides. In contrast, areas with lower tides could see sediment accumulation, forming new landforms or altering existing ones. Estuaries and deltas, which depend on precise sediment balance, will respond to these new forces. The deposition and removal of soil would shift the shape of coastlines and influence habitats for marine and terrestrial species. Tidal changes would also affect nutrient cycling in oceans. The vertical mixing of water, driven by tides, brings nutrients from deeper layers to the surface. A second moon could enhance this process in some regions, providing more nutrients for plankton and small fish. In other areas, interference between the moons might reduce mixing, creating localized nutrient poor zones. These variations would cascade through food chains, influencing fish populations, marine mammals, and seabirds that depend on predictable food sources. Sea level variations would become more dynamic. The timing of high and low water would no longer follow a simple schedule. Ports, harbors, and shipping lanes would need to account for more irregular tides. Water levels at coastal cities could fluctuate more than currently observed, affecting flood risk, sediment deposition, and human infrastructure. Areas prone to storm surges might experience amplified effects if high tides coincide with extreme weather, increasing coastal vulnerability. The second moon would also influence internal waves within the ocean. These waves occur when water of different densities interacts under tidal forcing. Multiple moons would create more complex patterns of internal wave propagation. Energy from these waves contributes to vertical mixing and heat distribution. Over long timescales, these variations could affect oceanic stratification and seasonal temperature layers subtly, altering climate dynamics and biological productivity. Polar regions would experience tidal effects as well. Ice sheets, sea ice, and coastal glaciers respond to water movement. Enhanced tidal forces could slightly accelerate ice flow at the margins or create larger openings in sea ice, modifying circulation patterns in polar oceans. The interaction between tides and ice would influence the transport of cold water to lower latitudes. These flows are important in regulating global climate by distributing temperature and salinity. Large scale phenomena like El Nino and La Nina rely on oceanic and atmospheric interactions. A second moon's effect on tidal mixing and currents could modulate the intensity and frequency of these events. Changes in the distribution of warm surface water might amplify or reduce the strength of weather patterns associated with tropical Pacific oscillations. Such modifications would occur over decades or centuries as the new tidal regime settles into predictable patterns influenced by the moon's relative positions. Shallow seas and inland water bodies would be particularly sensitive to the addition of a second moon. The Mediterranean, Red Sea, and the Baltic might see variations in tidal flow that differ from the open oceans. Narrow straits, like the Bosporus or Strait of Gibraltar, could experience more rapid changes in current speed. This could influence water exchange between basins, nutrient distribution, and the migration of marine species that rely on predictable currents. The energy of tides also interacts with coastal ecosystems. Mangroves, salt marshes, and tidal flats depend on the rise and fall of water for sediment deposition, nutrient delivery, and seed dispersal. A second moon would change these rhythms. Some ecosystems might see increased flooding and sediment transport, while others could experience less frequent inundation. The net effect would depend on local topography, orbital characteristics of the moons, and seasonal interactions. Tides are closely linked to the rotation of Earth. The addition of another moon would slightly increase tidal friction. This would gradually slow Earth's rotation at a faster rate than currently observed. The length of a day would increase, and the timing of tides relative to the sun would shift. Over millennia, these changes would feed back into tidal cycles, ocean currents, and even climate systems. The cumulative effect would be small on a human timescale, but measurable over geological periods. Estuaries and river mouths would see altered flow regimes. Tidal rivers rely on predictable daily highs and lows for sediment transport. Changes in tidal frequency could cause stronger backflows or more irregular flooding. Sediment deposition patterns would change, influencing river deltas, coastal plains, and the formation of new landforms. Long-term shifts might alter the habitat of fish, birds, and other species dependent on these regions. The combined effect of two moons on the oceans is a complex overlay of forces. Some tides would become extreme, while others would diminish. Currents would adjust in response to altered energy inputs. Coastal erosion and sediment deposition would follow new patterns. Polar oceans would react to modified ice and water movement. Shallow seas and estuaries would experience irregular flow, and ecosystems would adapt slowly to new cycles. The entire planetary water system would reflect the influence of an additional celestial body. Even subtle shifts in tidal amplitude can propagate across oceans. Waves traveling through large basins respond to variations in gravitational pull. Ocean gyres, the large scale circular currents, would adjust speed and path according to changes in water distribution. The rotation of Earth, combined with multiple tidal forces, would produce small but measurable shifts in the timing and location of major currents. The energy balance of the oceans would be altered gradually, but consistently. The second moon would affect storm surges and coastal flooding. High tides that coincide with strong winds or low pressure systems could raise water levels above current norms. The timing of these events would become less predictable, complicating planning for coastal infrastructure. Sediment transport during storms would change, influencing beaches, dunes, and river mouths. Over centuries, these modifications could reshape entire coastlines, producing new patterns of erosion and deposition. Global climate systems rely on the distribution of heat by oceans. Currents carry warm water to high latitudes and cold water toward the equator. A second moon would subtly change the strength and direction of these currents, modifying heat transfer. Seasonal temperature differences might shift slightly, affecting wind patterns, precipitation, and regional climates. The influence would be gradual but continuous, altering climate dynamics over long timescales. Ultimately, the interaction of two moons with Earth's oceans would be an intricate system of forces. Tides, currents, sediment transport, and coastal processes would all respond. Polar regions, shallow seas, estuaries, and open oceans would each experience changes specific to their characteristics. Ocean energy distribution, mixing, and nutrient cycles would adjust slowly. Climate and weather systems would reflect these altered flows. The addition of a second moon transforms the planet's hydrosphere in subtle but significant ways that accumulate over time. The addition of a second moon would create measurable effects on Earth's rotation. Tidal forces exerted by moons act as brakes, transferring energy from Earth's spin to the moon's orbits. With a second moon, this process would intensify slightly. The length of a day would increase at a faster rate than with a single moon. Each century, the day might lengthen by more milliseconds than currently observed. Over thousands of years, this would lead to perceptible changes in the timing of sunrise and sunset. The rotation rate is closely linked to ocean and atmospheric dynamics. Altered day length changes how energy is distributed across the planet, affecting climate and weather cycles. The axial tilt of Earth, which currently averages about 23.5 degrees, would experience subtle changes under the influence of two moons. The moon helps stabilize this tilt, preventing wide swings. A second moon introduces additional gravitational pulls that could shift the tilt slightly over long periods. These shifts might occur over thousands or millions of years. Even minor variations in tilt change the intensity of seasons. A tilt increase would make summers hotter and winters colder, while a decrease would produce milder seasonal differences. The distribution of sunlight across latitudes would adjust, influencing the amount of energy received by different regions. Atmospheric tides are directly influenced by the moon's gravitational pull. High tides in the air occur as molecules are slightly drawn toward the moon. A second moon would create additional atmospheric bulges. These variations in air pressure propagate as wind patterns, slightly changing prevailing directions and strength. The equatorial and mid-latitude jet streams, large bands of fast-moving air in the upper atmosphere, could experience minor shifts in position or speed. These shifts are gradual but continuous, contributing to variability in storm tracks, rainfall patterns, and temperature distribution. Wind patterns at the surface would respond to changes in pressure gradients caused by two moons. Regions near the equator, where centrifugal forces interact with gravitational pulls, might see small differences in trade winds. Mid latitude westerlies could adjust their paths. Monsoonal flows might experience slight timing shifts as the seasonal interaction between land heating and ocean temperatures responds to longer or more irregular tidal cycles. Even small changes in wind patterns influence precipitation, evaporation, and the movement of water vapor across continents and oceans. A second moon would influence the length of seasonal cycles in subtle ways. The timing of solstices and equinoxes is tied to Earth's tilt and orbital position relative to the Sun. Slight changes in tilt or rotation speed would alter when these events occur. Over long timescales, the distribution of sunlight between hemispheres might shift slightly. Northern summers could begin earlier or later, with small changes in peak temperatures. Southern winters might extend or shorten in response. These variations would be minor, but continuous, adjusting seasonal climate patterns across decades and centuries. Atmospheric circulation patterns, including Hadley cells and polar cells, are influenced by the distribution of solar energy and the rotation of Earth. Longer days or minor shifts in tilt would affect the strength and reach of these circulation cells. Tropics could experience changes in rainfall intensity and frequency. Subtropical deserts might expand or contract slightly depending on wind and precipitation changes. Polar regions could see variations in temperature gradients, influencing ice formation and melt cycles. These effects emerge gradually as the new tidal regime interacts with Earth's rotation and atmosphere. The speed of Earth's rotation affects the Coriolis effect, which deflects moving air and water. A slightly slower rotation increases the distance over which Coriolis forces act, modifying ocean gyres and wind trajectories. Tropical cyclones and mid-latitude storms could form along slightly different paths. Over long periods, small changes in storm frequency or intensity might result. The energy balance of the atmosphere would adjust slowly, reflecting the combined gravitational pull of two moons. The second moon would also influence local weather patterns. Coastal regions experience microclimatic effects driven by tides and winds. Stronger or additional tidal bulges in the atmosphere might slightly modify pressure patterns, producing subtle shifts in temperature, cloud cover, and rainfall. These effects are strongest near large bodies of water, but are measurable in inland areas as the atmosphere adjusts to new gravitational cycles. The interactions between tidal forces and topography create patterns that repeat with predictable timing, although altered compared to a single moon system. Global temperature distribution is affected indirectly by the presence of a second moon. Changes in rotation and axial tilt influence the angle of solar radiation received at various latitudes. Even a small shift in tilt modifies the energy balance, altering heating and cooling patterns seasonally. Ocean currents respond to these changes, redistributing heat differently. Equatorial regions could become slightly warmer during peak seasons, while polar regions might experience modified cooling. These temperature shifts are gradual and accumulate over many centuries, producing a slowly evolving climate pattern. Atmospheric tides from a second moon would interact with diurnal heating cycles. During the day, the sun warms the surface and creates pressure variations. At night, cooling occurs. The addition of a second gravitational pull would superimpose additional periodic forces. Air masses might rise or fall slightly differently, affecting convection. Clouds could form in altered locations, and rainfall distribution might change subtly. These adjustments are continuous, measurable, and would stabilize over long timescales as the atmosphere adapts to new tidal patterns. The two moons' gravitational effects also influence the exchange of energy between atmosphere and ocean. Tides create currents and waves, transferring energy into the air. A second moon adds another layer of interaction. Atmospheric pressure oscillates slightly in response, modifying wind, speed, and direction. This interaction links to rainfall, temperature, and cloud formation. The effects vary by region, influenced by latitude, topography, and proximity to large water bodies. Over time, the cumulative influence shapes regional climate dynamics. Changes in rotation rate influence the timing of day night cycles relative to seasonal progression. Longer days allow extended periods of solar heating in specific locations, potentially raising maximum daily temperatures. Nighttime cooling may be more pronounced if longer nights allow more heat to radiate into space. These variations affect soil temperatures, plant growth cycles, and the timing of ecological processes. The effects are subtle but measurable across decades and centuries. Atmospheric tides also affect stratospheric circulation. The interaction of gravitational pull with the upper layers of the atmosphere influences wind patterns and in the transport of ozone, water vapor, and aerosols. A second moon introduces additional periodic forces that can modify these flows. The changes are small, often less than a percent, but over long durations, they adjust the balance of heating and cooling in the atmosphere. Such variations have implications for climate modeling and long term weather prediction. The presence of two moons also has an indirect effect on precipitation patterns. Rainfall depends on temperature gradients, air pressure, and humidity. Tidal modulation of atmospheric pressure and wind patterns would slightly change where air masses converge and rise. Regions that previously experienced predictable wet and dry seasons might see small shifts in timing or intensity. These adjustments occur over many cycles of alignment between the two moons and the sun, producing a new rhythm in precipitation distribution. Subtle shifts in axial tilt and rotation speed influence the formation of storms. Tropical cyclones rely on warm water, wind shear, and Coriolis forces. A slightly slower rotation, or altered tilt, could change the latitude at which storms intensify or their track across oceans. Mid latitude storms may form along altered jet stream paths. These changes develop gradually and are reinforced over thousands of orbital cycles, producing a climate environment subtly different from the current system. The second moon would also affect seasonal heating in continental interiors. Without the moderating influence of oceans, land heats and cools quickly. Changes in the length of day and axial tilt slightly alter the rate of solar energy absorption. Summers could become marginally warmer, winters slightly cooler, or the timing of seasonal peaks shift. These variations influence evaporation rates, snowpack formation, and river flow timing. The impact is gradual but persistent across centuries. In conclusion, a second moon would influence Earth's rotation, length of day, and axial tilt. These changes would alter seasonal cycles, global temperature distribution, atmospheric, tides, and wind patterns. Subtle but continuous effects on weather, storm formation, precipitation, and temperature gradients would emerge. Over long timescales, the addition of a second moon would reshape atmospheric dynamics and climate systems in ways that are measurable and consistent, creating a new balance between gravity, rotation, and solar energy distribution. The addition of a second moon would change the appearance of the night sky. The phase of a moon depends on its position relative to the sun and earth. With one moon, the phases cycle predictably from new moon to full moon over approximately 29.5 days. A second moon introduces a separate cycle determined by its orbital period and position relative to Earth and the first moon. The two sets of phases would sometimes coincide and sometimes differ, creating a more complex pattern of light and shadow at night. When both moons are full simultaneously, nighttime illumination would increase significantly. The combined reflected sunlight would brighten the surface of Earth beyond the levels experienced under the current moon. Shadows cast by objects would overlap, producing variations in darkness and depth. Craters, mountains, and other surface features would create more intricate shadow patterns due to the differing angles of light from the two moons. Nighttime brightness would fluctuate more frequently, depending on the alignment of both moons and their positions in the sky. The relative sizes and distances of the moons also influence illumination. A smaller or more distant second moon would contribute less light than the primary moon. Its apparent size in the sky would be smaller, and shadows cast would be less pronounced. However, even a modest contribution of reflected light can change the behavior of nocturnal ecosystems. Animals that rely on darkness or moonlight for activity would encounter new light conditions. Predators and prey might adjust the timing of feeding or movement according to the changing illumination. Lunar phases of two moons would sometimes create unusual visual phenomena. When one moon is full and the other is in a crescent phase, light distribution across the skies would differ from the single moon system. Crescent moonlight adds partial brightness, producing softer shadows and diffuse lighting. The combined effect of two moons at different phases would create patterns that shift nightly. Over weeks, the night sky would change more dynamically than currently observed, with periods of intensified light alternating with dimmer nights. The interaction of moonlight with clouds would also be affected. Reflected light from two moons would illuminate clouds at different angles, altering their appearance. Cloud edges might glow more brightly or cast shadows in unusual directions. Nighttime visibility would vary according to weather conditions and the positions of both moons. Observers on Earth would notice that nights no longer follow a simple pattern of brightness increasing and decreasing with a single lunar cycle. Instead, overlapping cycles would create complex and shifting illumination patterns. Shadow lengths would be affected by the relative elevation of the moons in the sky. The higher a moon rises, the shorter the shadow it casts. With two moons at different altitudes, objects on the ground could have multiple overlapping shadows of varying length and direction. These shadows would move independently as the moons traverse their orbits. Nights with both moons present in the sky would display a network of shadows that shift in direction and intensity, producing a continuous variation in surface lighting. Nocturnal ecosystems are particularly sensitive to light levels. Animals that navigate, hunt, or mate by moonlight would adapt to the additional light. Insects that rely on low light conditions might alter activity patterns. Amphibians, which use darkness for mating calls, could experience shifts in timing. Birds that migrate at night might adjust flight paths or departure times in response to brighter or more variable night skies. Over generations, these changes would influence behavior, feeding, and reproductive cycles. The second moon could also affect the timing of biological rhythms tied to lunar cycles. Many species use the single moon's phase as a temporal cue. Spawning in some marine species, nocturnal foraging and hibernation cycles are synchronized with moonlight levels. A second moon would create overlapping cycles, potentially modifying the rhythm of these natural behaviors. Some species might adjust by following the brighter moon, or they might adapt to average light levels over time. The result is a more complex environmental signal that organisms must respond to for survival. The perception of night for humans, though, would also change. In areas with clear skies, the presence of two moons would make the night brighter and more variable. Astronomical observations would need to account for the additional reflected light, which could interfere with telescopic measurements or photographic imaging. Observers would notice more frequent variations in the apparent size, phase, and color of the moons. Eclipses and transits would occur with more combinations, providing opportunities to study celestial mechanics in a more dynamic context. Twilight periods could be slightly affected. While sunrise and sunset are governed primarily by the sun, reflected light from two moons could brighten the sky just before sunrise or after sunset. Shadows from the moons might be visible when the sun is below the horizon. This effect would be minor compared to sunlight, but noticeable in areas with clear atmospheric conditions. The additional light would modify visibility at dawn and dusk, influencing human and animal activities. The apparent motion of the moons across the sky would create shifting patterns of illumination. As each moon rises, moves across the sky, and sets, the intensity and direction of moonlight change continuously. When both moons are present, the night landscape would be illuminated from different angles at the same time. Observers would notice that objects cast multiple shadows moving independently. These dynamic light patterns would alter the perception of topography, such as hills, valleys, and trees, at night. Seasonal differences would influence the appearance of the moons. The tilt of Earth's axis affects the path of the moons through the sky. During summer or winter, moons rise and set at different angles. With two moons, variations in elevation would interact to create unique patterns in each season. The contrast between moonlight and darkness would shift slightly, affecting nocturnal light cycles and environmental illumination. These seasonal variations would be more complex than with a single moon, producing an intricate rhythm of night brightness throughout the year. The second moon would also affect human cultural observations. Historically, lunar calendars and festivals relied on the regularity of the moon. With a second moon, tracking cycles for timekeeping or navigation would become more complex. The ability to predict full moons, eclipses, and phase changes would require accounting for two interacting orbital periods. Observational astronomy would need to consider overlapping shadow and light patterns, phase alignments, and occasional near coincidences between the moons. Celestial events such as eclipses would occur more frequently and with varied timing. Lunar eclipses of one or both moons might take place, depending on alignment with Earth and the Sun. Solar eclipses could be partially or fully affected by the position of each moon. The interactions of shadows would produce unusual sequences of light and darkness, providing measurable data on the mechanics of multi-satellite systems. Scientists would use these events to refine understanding of orbital dynamics and gravitational influence. The second moon would also contribute to light levels in polar regions, where the sun remains low or absent for months. Its presence could illuminate ice and snow surfaces, creating reflections and shadows that vary with lunar phase. In areas of prolonged darkness, such as polar winters, even modest moonlight would affect surface visibility and animal movement. The interplay of two moons could slightly extend the time during which nocturnal activity is possible, influencing ecological processes in these extreme environments. Overall, two moons would create a complex system of light and shadow across Earth. Nighttime illumination would vary with the position, phase, and size of both moons. Shadows would overlap and shift independently. Nocturnal ecosystems would adapt to brighter and more dynamic nights. Human observation of celestial phenomena would need to account for overlapping cycles and additional reflected light. The night sky would become a continuously evolving display, structured by the positions and movements of two separate moons. The presence of a second moon would influence Earth's crust through tidal stress. The gravitational pull of a single moon already causes subtle flexing of the lithosphere. Land rises and falls slightly with the tides, though the motion is much smaller than that of the oceans. With two moons, these forces would interact. At times, the pulls of the moons would combine, increasing stress on the crust. At other times, the pulls might partially cancel, producing periods of reduced stress. The daily and monthly cycles of land movement would become more complex, reflecting the relative positions of both moons. Tidal stress affects faults and fractures in the crust. Areas of existing weakness, such as fault lines and plate boundaries, would experience variations in pressure due to the combined gravitational forces. Slight increases in stress could trigger minor seismic events, while reductions in stress would temporarily relieve tension. Over long periods, the frequency and timing of earthquakes might shift slightly, following patterns connected to the positions of the moons. These changes would be gradual and continuous, with no immediate large scale disruptions, but measurable by sensitive instruments. Volcanic activity could also be influenced indirectly. Magma chambers respond to variations in stress within the crust. Increased tidal flexing might slightly alter the pressure on magma, producing small but measurable changes in the timing of eruptions. In regions where volcanic systems are already near critical pressure, the combined effect of two moons could produce more frequent minor eruptions or trigger the release of gases. These changes would occur over geological time, reinforcing the natural variability already present in volcanic systems. The flexing of Earth's crust due to tidal forces is not uniform. Continental masses respond differently than ocean basins. Large, rigid land masses experience less vertical movement than thinner or more flexible areas. The gravitational influence of a second moon would alter the distribution of stress across continents. Regions along coastlines, where land meets ocean, would experience the largest variations. These stresses could affect sediment deposition, uplift, and erosion patterns over time, slowly reshaping topography on both local and regional scales. Tidal flexing also affects the movement of tectonic plates. The plates float on a viscous mantle and respond to forces applied at boundaries and across their surfaces. A second moon's gravitational influence would add small forces at multiple points. Over millions of years, these forces could influence the rate at which plates drift. Plates moving apart at divergent boundaries might experience slight accelerations or decelerations. Convergent boundaries, where plates collide, could see minor variations in pressure, affecting mountain building and subduction processes. Earth's rotation interacts with tidal stress to influence tectonic motion. Slower rotation, due to combined lunar pull, changes the distribution of centrifugal force across the planet. This affects the shape of the crust and the way plates move. Slight adjustments in rotational speed can alter stress patterns at plate boundaries, particularly along long fault lines like the San Andreas or the Mid Atlantic Ridge. These effects accumulate gradually, creating measurable but subtle shifts in tectonic behavior over extended periods. Ocean tides indirectly influence the lithosphere as well. The weight of water moving across continental shelves causes periodic loading and unloading of the crust. With two moons, tidal ranges could be larger or more variable. The alternating pressure on coastal lithosphere could affect fault stress, leading to slight increases in seismic activity in regions with high tidal variation. Estuaries, bays, and shallow seas would experience the largest influence, while deep ocean basins would see smaller variations. The combined gravitational pull also affects vertical displacement of the crust. Peaks and valleys might rise or fall by millimeters daily and centimeters over months. Over geological time, these small movements can contribute to the formation of folds, fractures, and minor uplifts. When the two moons align, the crust could flex more strongly than at other times, temporarily intensifying these processes. Patterns of uplift and subsidence would reflect the interaction of the moon's orbits with local geological structure. Continental stress patterns would respond to the second moon's orbit. Crustal plates are subject to uneven forces across their surfaces. The addition of a second source of gravity changes the orientation and timing of maximum stress. Areas prone to stretching, compression, or shearing would feel alternating pressures differently than they do now. The resulting shifts in stress could influence the formation of faults, the movement along existing faults, and the development of small-scale fractures in the lithosphere. In some regions, tidal stress might concentrate along fault zones. Over time, this concentration could produce a higher frequency of microearthquakes. These events would release energy gradually, modifying stress distributions across plates. While individual quakes would be minor, the cumulative effect could affect long term tectonic behavior. Plate boundaries that are already under high stress, such as subduction zones in the Pacific Ring of Fire, would be most sensitive to these variations. Volcanic arcs and hotspots respond to changes in lithospheric stress as well. The movement of magma through cracks and conduits is influenced by pressure in the surrounding rock. The addition of a second moon could slightly modify these pressures, creating periodic changes in magma flow rates. Over thousands or millions of years, these variations could contribute to altered eruption cycles, influencing the growth of volcanic mountains and the release of gases into the atmosphere. The flexing of the crust also interacts with mantle convection. Tidal stress produces minor but continuous deformation of the lithosphere, which can slightly affect the flow of molten rock in the mantle beneath. Changes in mantle convection patterns influence plate motion, volcanic activity, and the formation of geological features. While the forces from a second moon are small relative to internal Earth processes, their persistent action could produce measurable differences over extended geological time. Coastal regions are particularly affected by tidal stress. The shifting weight of ocean water exerts periodic pressure on adjacent land masses. A second moon, altering tidal amplitude and timing, increases variability in this loading. Shorelines may experience accelerated erosion in some cycles and sediment deposition in others. Over centuries, this alternation reshapes coastal plains, estuaries, and continental margins. The lithosphere responds by flexing slightly, redistributing stress across fault networks and sediment layers. Earthquakes in the interior of continents could also be affected. While most seismic activity occurs along plate boundaries, intraplate regions have faults that respond to stress changes. Tidal forces from two moons produce small periodic variations in stress. Certain alignments could slightly increase the likelihood of minor tremors in those regions. These events are generally small, but illustrate the wide ranging influence of an additional celestial body on Earth's geophysical processes. The interaction between two moons also influences tidal resonance in the lithosphere. Just as ocean basins resonate with tidal motion, large continental masses can flex in response to gravitational oscillations. Multiple moons create overlapping cycles of stress, producing more complex flexing patterns. Peaks of stress might occur when the moons align, while troughs occur when their forces counteract. These variations are subtle, but over geological time, they shape crustal deformation patterns and contribute to long term evolution of the lithosphere. Long term plate tectonic activity could be affected by accumulated tidal stress. Divergent and convergent boundaries, transform faults, and continental rifts all experience small modifications in force due to gravitational influence. Even minor adjustments in motion over millions of years contribute to the gradual rearrangement of continents. Mountains could rise slightly faster or slower depending on stress cycles, and rift valleys might develop along new orientations influenced by tidal flexing. In summary, the addition of a second moon would impose extra gravitational stress on Earth's lithosphere. Tidal flexing would become more complex, influencing seismic activity, volcanic systems, and fault behavior. Continental stress patterns would shift slightly, affecting intraplate regions as well as plate boundaries. Over millions of years, these forces could subtly alter the movement of tectonic plates, the timing of eruptions, and the formation of geological features. The Earth's crust would respond continuously to the combined influence of two moons, producing a dynamic but gradual modification of the planet's geological systems. The addition of a second moon would influence the environment of space near Earth. Every object in orbit responds to gravitational forces, including natural satellites and artificial objects. Currently, satellites travel through predictable paths influenced by Earth's gravity and that of the single moon. Introducing a second moon adds another gravitational source. The paths of satellites, space stations, and artificial debris would adjust slightly in response to these additional forces. Over time, these small perturbations could accumulate, altering trajectories in measurable ways. Artificial satellites in low Earth orbit would experience minimal immediate change, as the gravitational influence is strongest at higher altitudes. However, satellites in medium and geostationary orbits would feel more noticeable effects. Orbital mechanics dictate that even small changes in gravitational pull can shift a satellite's position over days and weeks. The second moon would cause deviations in orbit that must be tracked for accurate navigation and communication. Predictive models would need to include both moons' positions to ensure precise satellite placement. Debris from old satellites and rocket stages already present in orbit would also respond to the second moon's pull. Space debris moves at high speeds, and even small gravitational changes can modify collision probability. Objects in similar or intersecting orbits might cross paths more frequently. Areas of high congestion, such as the geostationary belt or low Earth orbit near popular orbital inclinations, would require updated calculations to maintain safe distances. Long term monitoring would become more important to prevent collisions and cascading debris events. The trajectories of satellites launched for scientific, commercial, or military purposes would need adjustment. Launch windows would consider the positions of both moons. Gravitational interactions could slightly change the speed required to reach stable orbits. Satellites on transfer orbits, moving between Earth and other locations, would experience small variations in energy requirements. Mission planners would incorporate these calculations to maintain orbital precision and to minimize fuel usage for corrections. Collision probability in orbit could increase subtly but measurably. When gravitational forces alter an object's path, intersections with other objects become more likely. Even a few millimeters of deviation per day, accumulated over weeks, could bring two satellites or debris pieces into closer proximity. Avoidance maneuvers would require more frequent monitoring and adjustments. Automated systems would need to include second moon effects for accurate predictions and safe operations. The second moon would affect near Earth dynamics for long term missions. Space telescopes, communication arrays, and scientific satellites in extended orbits could experience slight positional drift over months or years. Engineers would account for these variations in orbital station keeping strategies. The satellites relying on precise pointing or alignment would adjust periodically to compensate for gravitational influence, maintaining stability in observation, communication, or navigation tasks. The gravitational pull of two moons could produce resonance zones in certain orbits. These zones are regions where objects experience repetitive gravitational nudges. Satellites placed in these areas might gradually change orbit or gain energy in unexpected ways. Space agencies would need to avoid or carefully manage these regions to maintain safe satellite deployment. Over time, such resonances could also affect the stability of orbital debris, creating areas of higher concentration or dispersion. Space debris monitoring systems would become more complex. Radar and optical tracking networks must account for the second moon's position and influence. Predictions of potential collisions would include additional variables, including tidal gravitational perturbations from the moons. Satellite operators would rely on updated models to determine safe maneuver windows. Coordination among agencies and private operators would be necessary to manage traffic in orbit safely. Launch trajectories from Earth's surface would also adjust. Rockets leaving the planet encounter gravitational forces from Earth and the primary moon. The second moon adds an extra component that slightly modifies the optimal path for reaching orbit or transferring to lunar or interplanetary missions. While the change is small, fuel efficiency, timing, and mission safety all depend on precise calculation of gravitational effects. Engineers would incorporate these factors into planning, especially for sensitive or high value payloads. Satellites in polar or sun synchronous orbits would be affected differently than equatorial satellites. The gravitational influence of the second moon varies with latitude and orbital inclination. Polar orbits could experience slight changes in period and altitude over time. Sun synchronous satellites, which rely on consistent timing relative to the sun, would require periodic adjustments to maintain alignment. These adjustments would be small but continuous, emphasizing the importance of monitoring and correction in long term missions. Space debris from collisions or satellite breakups would interact more dynamically. With two moons, gravitational perturbations could slightly increase the chance of secondary collisions. Objects released from one orbit could drift into intersecting orbits of other debris or operational satellites. Over decades, these small changes could accumulate, affecting the density and distribution of debris. Active removal strategies would need to account for multi moon effects to maintain safe orbital environments. The second moon would also influence lunar missions and cislunar space. Rockets traveling between Earth and the moon must consider the combined gravitational forces. The addition of a second moon creates a more complex field, requiring updated navigation calculations. Spacecraft may need to adjust trajectory or timing to reach the intended lunar orbit safely. Cislunar stations and orbiting platforms would similarly be influenced, requiring precise tracking to maintain stability. Earth observation satellites would record slight variations in apparent motion. Imaging satellites would need to account for the effect of the second moon on orbital speed and position to ensure accurate geolocation. Even minor deviations affect mapping, remote sensing, and reconnaissance missions. The inclusion of second moon effects in planning and calibration ensures consistent data quality over extended periods. Global positioning systems would remain functional, but accuracy could be influenced by small changes in satellite positions. Corrections for orbital drift would incorporate the gravitational pull of both moons. Timing and signal prediction algorithms would include adjustments for subtle shifts. The reliability of navigation for aviation, maritime, and land based systems would depend on continuous monitoring of multi moon orbital mechanics. The presence of a second moon could also affect space based debris mitigation strategies. Satellites designed to deorbit defunct objects rely on predictable forces to maneuver debris into controlled reentry paths. With an additional gravitational source, planning these maneuvers requires updated modeling. Over long periods, slight perturbations might change the rate at which debris drifts into lower orbits, influencing the design and timing of mitigation missions. In summary, the addition of a second moon would influence near Earth space in multiple ways. Satellite orbits, the debris trajectories, collision probability, and mission planning would all be affected. Gravitational perturbations would require updated calculations for launch, navigation, and orbital maintenance. Resonance zones could create areas of higher risk, and long term missions would need continuous monitoring. The combined influence of two moons introduces a dynamic but manageable complexity to space traffic and orbital operations. The long term evolution of a two moon system would be determined by gravitational interactions and orbital mechanics. A second moon in Earth orbit would not remain static. Over time, tidal forces between Earth and both moons would transfer angular momentum, causing gradual changes in orbital distance and speed. Depending on its initial orbit, the second moon could slowly move outward away from Earth as the primary moon does. Alternatively, in certain configurations, it could drift inward, bringing it closer to Earth over tens of thousands or millions of years. These changes are slow but continuous, occurring over geological timescales. Tidal locking is likely to occur eventually. This is the process by which a moon's rotation slows until it shows the same face to its planet constantly as the current moon does to Earth. Both moons would experience tidal locking at different rates, depending on their size, composition, and distance from Earth. The larger and closer the moon, the faster it locks. A smaller or more distant moon would take longer to achieve the same effect. Once locked, each moon would present a fixed hemisphere toward Earth, creating consistent patterns of illumination and gravitational influence. Orbital resonance is another possibility in a two moon system. Resonance occurs when the orbital periods of the moons are in a simple ratio, such as 2 or 3 to 1. In this situation, the moon's gravitational pulls reinforce each other periodically, producing stable or semi stable orbits. Resonances can prevent close encounters between moons and reduce the risk of collision. However, resonance can also increase tidal stress on Earth, particularly when the peaks of gravitational force coincide, amplifying flexing in oceans and crust over time. Such interactions would continue for thousands or millions of years, gradually shaping the system. Escape scenarios exist as well. If the second moon formed too close to Earth or was introduced at an unstable orbital position, gravitational interactions with Earth and the primary moon could eventually eject it from orbit. In such cases, the moon could become a small planet orbiting the sun, similar to an asteroid. The process is slow, and ejection would require cumulative gravitational perturbations over long periods. Earth itself would remain largely unaffected in terms of rotation and tides once the moon escapes, but prior fluctuations would leave lasting effects on climate, ocean currents, and the lithosphere. Collision between the moons is a low probability but possible outcome. If orbital paths intersect due to gravitational perturbations or orbital decay, a collision could occur. The result would be a massive redistribution of material, producing debris that might form a ring system or smaller moonlets. Any collision would also impact Earth through increased meteorite influx and temporary changes in tidal dynamics. Over millions of years, such events could reshape the near Earth space environment and alter orbital debris patterns significantly. Geological consequences of a two moon system would evolve gradually. Increased tidal stress would affect the lithosphere, contributing to subtle changes in earthquakes, volcanic activity, and crustal deformation. Over millennia, continental stress patterns would adjust, affecting mountain formation, rift development, and shoreline dynamics. Ocean tides would remain stronger and more variable, influencing coastal erosion, sediment deposition, and the distribution of marine habitats. The interplay between Earth's rotation, axial tilt, and dual lunar gravitational forces would shape long term climate trends. Climatic consequences would also develop slowly. Changes in axial tilt due to gravitational interactions with two moons could influence the severity of seasons over millennia. Ocean currents, driven by tides and wind patterns, would adjust to modified lunar cycles. Polar ice coverage might fluctuate in response to altered tides and seasonal energy distribution. Heat transport across latitudes could shift subtly, influencing precipitation, storm frequency, and temperature gradients. These effects would accumulate gradually, creating a new long term balance between climate systems and tidal forces. The comparison to known two moon systems in the solar system provides useful insight. For example, Mars has two small moons, Phobos and Deimos. Their orbits are irregular and influenced by tidal forces. Phobos is slowly spiraling inward and will eventually either crash into Mars or break apart. Deimos moves outward gradually. Studying these moons offers an example of how multiple satellites interact with a planet over long timescales. Earth's larger mass and stronger gravity would produce different rates of orbital evolution, but the principles are similar. Tidal forces, resonance, and orbital perturbation drive slow changes. Other giant planets, like Jupiter and Saturn, host multiple moons of varying sizes in resonant orbits. These systems demonstrate long term stability achieved through careful orbital spacing and periodic gravitational interactions. Some moons maintain synchronous rotation, while others experience orbital shifts over time. Earth's hypothetical second moon would eventually find a similar equilibrium, or undergo slow migration, influenced by the combined gravity of Earth, the primary moon, and the Sun. The dynamics would be measurable, but gradual. Over millennia, the system would settle into patterns of relative stability. One moon might maintain a slightly closer orbit, while the other remains further away. Tidal locking would keep rotational periods synchronized to the planet. Resonances could maintain orbital spacing that reduces collision risk. The moons would continue to exert gravitational influence on Earth's oceans and crust, shaping tidal behavior, seasonal cycles, and geological activity in slow, ongoing patterns. Orbital simulations suggest that extreme instability is unlikely if the second moon begins in a carefully selected orbit. Minor adjustments in orbital eccentricity and inclination would stabilize over time. The moons would maintain consistent periods relative to each other, producing predictable tidal interactions on Earth. Climate, ocean currents, and crustal stress would reflect the cumulative effect of the dual gravitational sources, resulting in a more complex but measurable natural system. The second moon's presence would create new long term opportunities for observation and study. Astronomers and planetary scientists could measure orbital evolution, tidal effects, and resonance interactions in real time. Observations of changes in Earth's rotation rate, axial tilt, and crustal flexing would provide insight into multi moon dynamics. This system could serve as a model for understanding the behavior of satellites in other planetary systems. The interplay between the moons would also influence the evolution of Earth's oceans. Tidal energy would vary depending on the alignment of the moons. During periods when both moons exert maximal tidal pulls simultaneously, ocean bulges would be higher than normal. When the moons are opposed, tidal range would decrease slightly. These fluctuations would modify coastal environments over thousands of years, shaping sedimentation, estuaries, and shoreline morphology gradually. The long term evolution of a two moon system is governed by slow, continuous processes. Tidal forces adjust rotation, orbital resonance stabilizes periods, and gravitational interactions redistribute energy. Collisions or escape events are rare but possible, producing sudden changes. Geological and climatic consequences accumulate over millennia, modifying Earth's crust, oceans, and atmospheric patterns. Comparison to other multi moon systems demonstrates that stability can persist for millions of years, but the system remains dynamic, adapting to the ongoing gravitational interactions. The addition of a second moon would change the framework used for observational astronomy. Currently, astronomers rely on the moon as a consistent reference point for measuring positions and motions of stars, planets, and other celestial bodies. A second moon introduces an additional moving point in the sky, altering the relative geometry used in observations. The moon's positions would need to be tracked precisely to maintain accuracy in measurements. Predicting their orbits becomes necessary for calculating angles, distances, and timing for observations of distant objects. Eclipses would occur more frequently and with greater variation. A solar eclipse happens when the moon passes directly between Earth and the Sun, casting a shadow on the surface. With two moons, each could independently block the Sun. Occasionally, the moons could align, producing unusual patterns of shadow and light on Earth. Lunar eclipses would also be affected. One moon could pass through Earth's shadow, while the other remains visible, creating complex sequences of illumination. These events would be predictable, but require detailed modeling to understand timing and coverage. Occultations, where the moon passes in front of stars or planets, would be influenced by dual moons. Observers would note more frequent occultations as each moon moves through the sky at its own rate. Transit phenomena, in which celestial bodies pass in front of distant objects would become more variable. Astronomers would need to calculate combined lunar positions to interpret observations correctly. The overlapping motion of two moons produces a more dynamic background for tracking other celestial events, requiring precise timing and orbital modeling. Early navigation and historical astronomy would have been affected as well. Sailors and explorers used the moon for nighttime orientation, noting phase, position, and rising times. Two moons would complicate these calculations. Determining latitude and longitude based on lunar observations would require consideration of the relative motion of both moons. Nighttime charts would include the predicted positions of both satellites. Over time, humans would develop methods to account for the additional moving reference, refining navigation techniques to maintain accuracy. Timekeeping systems, dependent on lunar cycles, would need adjustment. Calendars using the moon as a marker of months would require consideration of two independent cycles. Cultural and practical applications of moon phases, including planting, hunting, and rituals, would experience overlapping signals. Predicting the timing of specific lunar phases would involve understanding the interaction between the orbital periods. Historical societies would adapt to these patterns over generations, producing more sophisticated observational records. The apparent motion of the moons in the sky affects telescopic observations. Telescopes fixed on distant stars or planets rely on precise alignment. The gravitational interaction of the second moon with the primary moon and Earth slightly shifts Earth's rotation and orbital motion. Even small changes affect the angular position of observed objects. Observers must compensate for these shifts to maintain accurate tracking. Long-term observations of star positions and planetary movements would require models that include both moon's influence on Earth's rotation and tilt. Astrophysical calculations of Earth-Moon interactions would become more complex. The exchange of angular momentum between Earth and two moons affects rotation speed, orbital eccentricity, and axial tilt. Scientists modeling tides, precession, and orbital evolution would need to include dual lunar forces. Predictive equations for future positions of the moon, tides, and rotation changes must reflect the interactions between both satellites. Over centuries, these calculations provide accurate forecasting for astronomy and space operations. Observations of celestial mechanics would provide opportunities for research. Measuring how the moons influence each other's orbit would reveal the dynamics of multi-satellite systems. Astronomers could study resonance effects, tidal locking, and orbital precession in real time. Earth-based observations would capture subtle changes in the apparent speed, path, and distance of each moon. Comparing these results to models of other planetary systems enhances understanding of how moons interact with their parent planets over long periods. Lunar parallax, the apparent shift in position of a moon against distant stars when observed from different locations on Earth, would need recalculation. Each moon produces its own parallax effect, which would influence geodesy, cartography, and spatial measurements. Accurate mapping of Earth's surface using lunar reference points would require tracking both moons simultaneously. Over time, instruments and observation techniques would adapt to account for two dynamic reference points. The presence of two moons would influence predictions of tides in relation to astronomical events. Observing lunar and solar alignments is essential for studying tidal resonance and energy. With dual moons, the timing and intensity of tidal peaks and troughs would vary according to the relative positions of the moons. Historical attempts to correlate lunar cycles with tidal behavior would have been more complex, requiring detailed records and careful observation. Modern scientists would analyze these patterns to understand combined lunar effects. The moon's combined influence would affect the calculation of orbital perturbations for other celestial bodies. Planets, asteroids, and comets experience slight changes in trajectory due to gravitational forces. Introducing a second moon slightly modifies Earth's gravitational field. Predicting the motion of nearby objects in the solar system would need to include the second moon's contribution. Refining models of orbital dynamics and collision probability, observers would account for these small but significant forces in calculations. In practical astronomy, the second moon would require updated star charts and ephemerides. These charts indicate the positions of celestial objects for navigation and observation. With two moons, predicted positions of planets, stars, and artificial satellites would include gravitational interactions from both moons. Observatories would need to track the moon's motion continuously. Astronomers and navigators would combine observations with models to maintain accuracy over short and long timescales. Finally, the dual moons would provide a living laboratory for studying tidal effects on Earth and orbital evolution. Observing changes in rotation rate, axial tilt, and orbital paths would enhance understanding of planetary mechanics. Combined with historical records, these observations allow scientists to reconstruct long-term patterns of lunar influence. The system demonstrates the complex interplay of gravity, motion, and celestial observation in shaping both natural cycles and human understanding of the night sky. The presence of a second moon would produce wide-ranging effects across Earth's environment, oceans, atmosphere, and space environment. Tidal forces from both moons would combine in varying ways, producing cycles of higher and lower tides across the globe. These cycles would influence ocean currents, coastal erosion, and sediment deposition, slowly reshaping coastlines over centuries. Tidal bulges would occur in response to the alignment of the moons, creating periods of strong combined pull and periods of partial cancellation. The distribution of water across the planet would adjust to these patterns, contributing to subtle changes in ocean circulation and energy transfer between equatorial and polar regions. Earth's rotation would respond to the gravitational pull of two moons. Angular momentum exchanges would produce slight changes in the length of the day over long periods. The rotation might slow more quickly or unevenly depending on the relative position of the moons. Over millennia, these variations could affect climate cycles and seasonal timing. The axial tilt, while largely stable, would experience minor fluctuations influenced by the combined gravitational forces. These variations would slightly alter the intensity of seasons and the distributions of sunlight across latitudes, affecting temperature gradients and weather patterns over time. Atmospheric systems would also be influenced by dual lunar forces. Tides in the atmosphere, caused by the moon's pull on air masses, would become more complex. Wind patterns could vary in response to these subtle changes, affecting storm tracks, monsoon timing, and the movement of pressure systems. Cloud formation and precipitation patterns could shift slowly, following the modulation of tidal forces and seasonal solar heating. Over centuries, the integration of lunar influences with Earth's atmospheric dynamics would produce a slightly altered climate rhythm compared to a single moon scenario. The Earth-Moon system itself would evolve under these dual forces. Orbital resonance and tidal locking processes would determine long-term stability. Each moon would gradually adjust its orbit in response to Earth's gravity and the other moon's pull. In the case of resonance, both moons could maintain predictable positions relative to each other, reducing collision risk and providing stable cycles of tidal influence. In the absence of precise resonance, small adjustments in orbit would occur continuously, producing slow variations in gravitational force on the planet. Geophysical effects would accumulate in the lithosphere and oceans. Crustal flexing would reflect combined tidal stresses, influencing fault activity and the timing of minor earthquakes. Volcanic systems might experience subtle changes in eruption frequency, guided by variations in lithospheric pressure. Oceanic tides and currents would shift with the moon's relative positions, producing complex but predictable patterns of energy movement and coastal influence. Over thousands of years, the cumulative effect would be measurable, affecting geological processes and sedimentary layering across continents and continental shelves. The astronomical implications would be significant. Observational astronomy would adjust to the presence of two moving reference points in the sky. Eclipses, occultations, and transits would follow more complex patterns, with the moon's positions determining timing and coverage. Celestial navigation, historically dependent on the moon, would require new models for accurate determination of latitude, longitude, and timing. Ephemerides would include dual lunar positions to predict celestial positions accurately. Astrophysical calculations would incorporate interactions between Earth, both moons, and the Sun, refining predictions for tides, rotation, and orbital behavior. Integration of tidal or rotational and orbital effects highlights the interconnected nature of Earth's systems. The motion of the moons affects tides, which in turn influence currents, which then interact with climate and atmospheric patterns. Changes in rotation speed and axial tilt feed back into seasonal timing and energy distribution. The system is dynamic, with multiple forces operating simultaneously, yet producing a coherent, stable planetary environment. Earth's natural cycles would adjust, maintaining long-term stability while reflecting the influence of an additional satellite. Comparisons with known multi-moon systems provide context. Planets like Mars, Jupiter, and Saturn illustrate the variety of ways multiple moons interact with their parent planets. Resonance, tidal locking, and orbital perturbations are common features. Earth, with its stronger gravity and larger primary moon, would experience similar processes on longer timescales. The presence of a second moon would produce measurable differences, but would not destabilize the system immediately. Over millennia, the system would reach a form of equilibrium where both moons coexist in predictable orbits, exerting consistent gravitational influence on the planet. The broader implications extend to oceanic and climatic stability. Although tidal ranges would increase and currents would adjust, the planet's climate would remain regulated by solar energy and the fundamental distribution of heat. Seasonal cycles would continue, modified slightly by changes in axial tilt and rotation. Geophysical processes would adapt to the new pattern of gravitational forces. Erosion, sedimentation, and tectonic activity would reflect combined lunar influence, but the overall planetary system would maintain continuity of structure and function. Space systems would also adapt to dual moons. Satellites and debris would require updated monitoring and trajectory prediction. Orbital resonance zones would define safe paths for navigation and deployment. Future space exploration would consider the presence of two moons for mission planning, trajectory calculation, and launch timing. The environment of near Earth space would become slightly more complex, but engineering solutions could maintain operational safety and precision. The synthesis of these factors illustrates the interconnected consequences of adding a second moon. Tides, rotation, axial tilt, lithospheric stress, ocean currents, atmospheric patterns, and astronomical observations all respond to the same gravitational influences. Over long periods, the integration of these effects produces new cycles of natural activity while preserving the overall balance of the Earth system. The planet adjusts gradually, demonstrating resilience in the face of altered celestial dynamics. In conclusion, the presence of a second moon would produce measurable and predictable changes across Earth's environment and space. Tidal forces would strengthen and diversify, rotation would adjust, axial tilt would fluctuate slightly, and orbital resonance would establish long-term stability. Geological, climatic, and astronomical systems would integrate these influences, maintaining coherent patterns while adapting to new dynamics. Comparisons to other planetary systems confirm that multiple moons can coexist without destabilizing a planet. Earth would continue its natural cycles, now influenced by an additional satellite, producing a slightly more complex, yet stable planetary rhythm. Through the combination of tidal, rotational, orbital, and gravitational effects, the presence of a second moon offers insight into the delicate balance of celestial mechanics. It demonstrates the way multiple forces interact to shape a planet's environment, how natural systems adjust to persistent external influence, and how long term stability can coexist with dynamic change. Earth's oceans, crust, atmosphere, and sky would reflect the continuous pull of two moons, maintaining ongoing cycles that define the planet's character while introducing new patterns to its natural rhythms.